There it is. Hey, now it works. Yeah, Grant's not going to be happy. That's okay. You can read through it. All right, so question, we had a biological question. Are bats attracted to water? Statistical question was, do bats visit water more than bare ground? Okay, let's change it. Because our biological question, or our statistical question, should be structured in such a way that we can actually reject it. We can use statistics to reject it. So in order to we can't really reject, is it more than the other? Because we don't know how much more. But we could say, is the frequency of visits to water equal to the frequency of visits to bare ground? Because now at that point we have a distribution. We could say it should be 50-50. And then based on what we see, we can see, well, how likely is it to actually get what we observed if there is no preference? Now we set up the statistical question that allows us to use statistics and obtain a p-value that basically says, here, this is the probability that we actually would see our data if there was no difference. If we have a really small probability, then yeah, chances are they're not equal. So bats would show a preference, which I think that's what you're hoping for, right?
Yeah, well, I'm not using real water. I'm just using, plastic wrap.
So you're
Yeah, tricks them,
but same idea, right?
Yeah.
Same idea. All right. So typically, as we create this statistical question, we're doing this. All data came from the same population. That's really our start. The start for that statistical question. What is the implication of that? What is our implication? We say all of our data that we've collected, and we measured, we recorded what groups they were in, we recorded when we collected them, we recorded when we collected, how we collected them, all of that stuff. If they all came from the same population, what's the implication?
It should be a good representation.
What's that?
It should be a good sample of the representation of the population.
Okay, so it'll be a represented.
It's
Yeah.
random. It's true.
It's random.
No significant difference between the animals.
What do you mean no
Difference.
So if all of our, so to kind of take a step back, we're going to use bats, right? All right. And this time we see this trend where they do favor water, but you have some bats that just smash the ground and then fly, all right? Who knows, all right? But when you look at them, those bats, all right, you got one group, and then you've got a second group. You say group A and group B. All right? You say, well, I think these are two separate groups. There's something different with this group that seems to be smashing into the ground. All right? Our assumption to test if they are different groups is to say that they all came from the same population. That this group classification is completely arbitrary. If that's the case, our population has a parameter. Has parameters associated with it. It has a mean, it has a sigma. If these belong to the same population, then these things have their own mean and standard deviation. But because they came from the same population, then our our sample statistics are going to be equal, and they approximate our population parameters. So it's the same idea as saying there's no difference. If they all came from the same population, then they should exhibit the same sample statistics. The same mean, the same variance, the same median, the same proportions, the same whatever. That then allows us to figure out, hey, whatever we do see, the means that we do see, how far are they from this scenario? and assign a probability. This is how likely it is to get this just from a random sample. Because again, if you take a random sample, you could get different numbers. We just want to know how likely is it to get those numbers just from random chance. So we have the statistical question. All right. From that statistical question, we're going to phrase it. We're going to know what kind of test we can run to generate these p-values. So you're going to get the test statistic. You're going to compare that test statistic to the null distribution. That gives us our p-value. That gives us our value of how likely is it to observe our data, or more extreme data, if the assumptions of our null hypothesis were true, meaning if they actually did come from this same group. From that answer, then, from that statistical answer, we can then go back to our biological question. Do bats prefer water? Yes, they do. Do plants prefer water over plastic? Who knows? Who knows? Hopefully, we get enlightened next year. And if we're still doing virtual, all those that graduated, join in. Ask questions. Stock up questions now. All right. So we do our test. What do we report? There's 5 things. We have to report what statistical test was performed. We have to give the test statistic. We have to give the degrees of freedom. We have to give the p-value. And we have to give the conclusion, or the interpretation of the test. You've seen this when you've read papers, scientific papers. You'll see what test was run. They'll give you this test statistic, this F. They'll give you degrees of freedom. They'll give you your p-value. There's a conclusion or interpretation built in. Now, my question is, which of these are optional and why? As I say, these are 5 things to report. You should always report these 5 things if they're available. So which ones end up becoming optional? Why? Like which one? So, answer is some of them don't have a test statistic. They just give a p-value. Which one?
Yeah, the permanent, I don't think that.
Yeah, permutational. A lot of our permutational or randomization tests, they don't have a test statistic. They didn't make any assumptions to generate a null distribution that test statistic should follow. We created our own null distribution, so we report the p-value. It didn't have a test statistic. What didn't it have then? Degrees of freedom. We didn't have degrees of freedom with it. So with our randomization tests, we report the test, we report our p-value, we report our conclusion. With the randomization test, we also have to say how many iterations we did. That's part of the methods section. All right, that's in one case. What would be another test that doesn't have all of these? Maybe it has 4 of these?
I mean, I was thinking degree freedom.
Yeah, some tests, the permutational test, but what other tests wouldn't have a degree of freedom? Do we do any exact tests? I think we did. Yeah, we gave it as an example. Gave it as an example. That was one that suffered, got cut because of all the crap that happened. We have exact tests. So if we work with discrete data, especially the dichotomous data, we know the actual probability distribution. We don't have to approximate it. So what we can do is calculate an actual probability of getting data as extreme or more extreme. Like we can calculate the probability of getting of rolling a 12 on in Monopoly. That's a given. Right? It's a well-defined probability. So for that, we didn't have degrees of freedom. We didn't have test statistic. Shapiro-Wilks test, normality test, had a test statistic. It had W, but it didn't have a degrees of freedom associated with it. So in R, thankfully, when we run these tests, if there is a test statistic, if there is a degrees of freedom, it will be listed in the output. That material needs to be included. That needs to be reported. All right? All right, so here's a general flow chart, very broad. All right? If we have one variable, we just went out and measured world counts on a ship. One variable. What type of variable is it? All right, so it's discrete. All right, quantitative. I'll say we'll lump it into continuous because we can analyze discrete data just like continuous data. So what are our test options then? Could do a one sample t-test, could do a z-test. Right? That's our test options. What happens if you did, you collected them from different locations, right? Location, where these shells were collected. What type of variable was that? Categorical. What are our test options? Goodness of fit test. Now, how many goodness of fit tests do we have? We got several. We'll go over them. Right? But broad categories is a goodness of fit test. Did our locations match some expected frequency? Some expected proportion. Two variables becomes a little bit harder because these two variables could both be categorical. They could both be continuous or numeric in some way, or you could have one categorical and one continuous. Now, in the broadest sense, one of those variables will be the independent variable and one will be the dependent variable. All right? So if we have that case, one categorical and one continuous, that's typically what you think of. We've got this grouping category, and then we have a measurement variable that we've measured. What's available to us? T-test and ANOVA. All right, both of those tests are testing means. If we flip it and we say these, they're reversed, so we have continuous measurement variable and then a categorical. Now we've kind of flipped it to more of like a discriminant analysis. All right. But it still didn't change the fact that we had two variables, one categorical, one continuous. If we have two continuous variables, then we're really kind of looking at correlation and regression analysis. If we go that next step and say that these aren't necessarily X and Y values, maybe these are both Y, it changes what types of tests start to do like classification at that point, trying to see relationships between those. We probably won't get to any of that. If we have two categorical variables, then we're looking at contingency analysis. So we're looking at things like location in which those snails were collected and maybe a season if you're doing world. All right, those are both categorical variables. We can look at their relationship. Is world length, independent of those two measures? Once we start getting to two or more variables, now we just go to this broad term called multivariate method. And this is one that I think some of you have come in to ask me, hey, what test should I run for my thesis? Right? And it's always, well, what variables are you measuring? And sometimes I just say, we're going to do multivariate methods of analysis. Now, some reviewers don't like that. Some faculty members don't like that. They need to know exactly what we're going to do. And unfortunately, it's kind of difficult because we don't know what types of data you're actually going to measure. What are we going to have? How many data points are we going to have? This multivariate methods could be anything from classification methods, could be multiple regression analysis, just a lot of stuff. We will get to this, all right, in the form of we have one measurement variable that we measure, and then we have a slew of other variables. How do we figure out what terms are most important at predicting that variable of interest? So we'll learn how to do that. And then I didn't even talk about the non-parametric or permutational versions of these tests. So the t-test, they've got non-parametric version of a t-test, a non-parametric version of ANOVA. You've got randomization methods of all of these. This is, but this kind of flow chart is telling you, start here. How many variables? What are their types? What tests are available? All right. So once you do choose a test, how do we run it? So we chose the test. That test has assumptions usually. All right. So then what you're going to have to do is check your assumptions. Typical assumptions, data are random and independent. All right, we'll see if we get to that violation. Hopefully we do at the end, but we'll see. All right. Second assumptions, typically data are normally distributed. All right, depending on how many variables we're looking at normality within each of our groups. And it could become exponential how many groups we're comparing. And the third most common assumption is equal variances. All right. If all of these assumptions are met, or if all of the assumptions of the test are met, then go ahead and run the test. We can run the test, and we know that whatever results we get, they're going to be valid. If we violate any of those assumptions and we still run the test, we can't trust those results. Because those assumptions are allowing us to compare our test statistic to some theoretical distribution. If we violate the assumptions, our test statistic no longer follows that distribution, and thus we'll come up with incorrect results. What happens if we don't meet the assumptions? Well, you've got really two different choices. One is probably the one you don't want to hear, and that's go back to the drawing board. Redesign your experiment, rerun it. No one wants to hear that. That's why there's been a lot of effort to come up with alternatives, which is basically choose a new test. Do something that doesn't have those assumptions, or choose a test that is robust against that violation that you have. All right. Most likely scenarios would be these non-parametric tests. At least that was the common choice, I'm going to say 20, 30 years ago. At least 20 years ago, maybe longer. I think I was doing randomization tests in grad school, so might be pushing 25 or 30. The non-parametric tests were the choice because they were fairly easy to do. We had computers, or we had mainframes that would do it, and even at the time, Windows 95 computer had Excel that can run a couple of these non-parametric tests. Now, the encouragement is to run these randomization tests. We have the computing power to do it, and to do it in a reasonable amount of time. So that's what we're going to be doing. All right. Questions? Quick overview. What I encourage you to do is look back to the undergrad section and look at those 3 handouts for the end. That was kind of marking our spot, kind of wrapping up what we were doing and in what direction. We will get to those and go through these flow charts again as we get to the test. So what's on our plate? On Wednesday, we're gonna move to the second presentation, which is reviewing descriptive statistics. You'll get hands-on in R, open RStudio, working in RStudio, importing data sets, calculating summary statistics, that sort of thing. All right, and then we'll probably finish all of that and start our review of statistical tests. These are all tests that you should have already covered. T-tests, Z-test, T-test, Z-tests, some variance tests, and so forth. All right, and then when we get to the ANOVA, that's its own presentation. We'll spend quite a bit of time reviewing, checking the assumptions, doing post hoc tests. I mean, there's a lot to do with the ANOVA. All right. All right, and I guess I could post this up. Unfortunately, the audio doesn't